All right, it is 10 o'clock. Good morning, good noon, and good afternoon to everyone joining us on the webinar today. My name is Bastian, I'm with Unisense Environment, and I'll be guiding you or us all through the webinar today. Our topic is going towards carbon neutral wastewater treatment. Obviously, the topic that you've all signed up for is nitrous oxide measurement and mitigation. We can look forward to getting insights on the state of the art of how to do that in real wastewater treatment plants and really see practical insights from experts on realized measurements and mitigation campaigns from our experts today. The group of participants is really diverse, really great. We have people from 10 different countries signed up all over the world, all the way from Denmark, Sweden, Norway, UK, Netherlands, Germany, Italy, US, Canada, and even Australia. So that really shows how this important topic is becoming a focus of intention in the wastewater sector, and how greenhouse gas mitigation is gathering in importance. Yes, without further ado, let's have a look at the agenda for today. Before I forget it, because I might otherwise forget it, feel free to follow us on LinkedIn if you like to hear more about similar webinars in the future, and in general be updated about our results from practical measurements that we or our customers are sharing. We are all about sharing results and working together. So if you want to stay in touch, follow us on LinkedIn, and if you happen to be in Sweden next week, then please come visit us in Jönköping at the VA Messen at our stand. For our speakers today, we have 4 excellent speakers. First, Christian and Sara from Sweden. They will both give a bit of a longer presentation, sharing their insights from their work. And afterwards, we have twice Mikkel from Denmark with a little shorter presentations. Combined, these experts have more than 50 years of experience in applied wastewater work, applied research, and actual running of wastewater treatment plants. So I think it's really great that they are here today to share their experiences with us, and that we can all learn from it. A few small points on housekeeping, how to run this webinar. I would like to ask everyone who is not a presenter to keep their camera shut off during the webinar. And then also, of course, to please stay muted unless you are asking a question. If you want to ask a question during the presentation, we'll have a dedicated time for that after each presentation slot. You can type your questions in the chat at any time, and that will mean that I will read them out afterwards. Or you can, in the time after the presentation, raise your hand, use that little raise hand button, and then I will ask you, call you out to unmute yourself and ask the question yourself. A recording of this whole session will be shared by email. So there you can, of course, you're welcome to take notes, but you don't need to take pictures of the slides or anything like that. We will make that available to everyone who is signed up. Right, and from here on, I would like to go ahead and introduce our first speaker for today. That is Christian Baresel. Christian is a research manager at IVL, the Swedish Environmental Research Institute, and he manages a big division of R&D activities, mainly at the Hammarby Sjöstadverk testing facility. Has a total of more than 15 years of experience in applied wastewater research. And I'm very much looking forward to your presentation, Christian. The floor is yours.
Okay, thank you very much. Now you can all see my slides?
Yes, we see it well.
Perfect. Okay, as I was already introduced, my name is Christian Baresel. I'm facility manager and coordinator for our pilot facility in Stockholm, Hammarby Sjöstadverket, where we, since 2008, are testing with help of different pilots new technologies within wastewater treatment, water reuse, sludge handling, and so on. And I would like to share some of our experiences with the greenhouse gas emissions. We have been working with that since the start at our pilot facility, more or less. And I would like to put up some aspects that relate to the greenhouse gas emission, and mainly with the focus of nitrous oxide emissions, of course, and how we implement that into our work and the different projects we have. But first, I would like to go back a bit. I don't know how many of you have been working with greenhouse gas emission measurements, but if you look back like 12 years back, then it wasn't really a happy time for us measuring greenhouse gas emission. It was quite often frustrating, extreme time consuming. The equipment wasn't just in a state that was suitable for the environment and the wastewater treatment, I would say. You needed extensive pre-treatment of your samples. You were more or less continuously calibrating the instruments, zeroing it. So it was really like a huge amount of work just to do some simple measurements. The data handling at that time wasn't that easy either. So and then often the results also were quite limited, as we had high uncertainties and only had response times that were really long and so on. And some of the equipment was quite fragile. On top of the slide here, you can also see the Unisense prototype, the first water sensor, for example. We have been working with that in our pilots as well, and it felt like we broke these sensors like 10 times per day. So we had a really huge consumption of these sensors. But that was then in the beginning. Time goes on, equipment evolves, and now here we have the standard sensor from Unisense, for example, now used in different processes in Sweden and our pilots. So during the last 10 years, there has been happening a lot. We have right now, I would say, quite advanced, robust instruments, and not only for measuring the water phase, also in the off gas. So we have instruments that are automatically switching range if the measured concentrations go into a different range in order to adapt the accuracy of the instrument. We have some of the instruments, so analyzers don't need any sample preparation anymore. They are automatically compensating for interferences with other gases, with the humidity. So we have really much better, much improved conditions in order to go out and measure greenhouse gas emissions. We have in our equipment, for example, what we often used is like the floating sample chambers. This is one we build them ourselves, but you see here it's quite advanced sample hood where we can control the flow over the hood in order to measure in all different kind of conditions like aerated, non-aerated, intermittent aerated processes, equipped with different sensors in the water as well. You see here, for example, the Unisense water sensor. We have also controlling of the DO, ammonia, nitrite, and so on, so that we can also follow up the processes while we are measuring. We have option to even dilute the gas flow in cases we really measure high concentrations and so on. So it's equipment that has evolved during many years of work, and also nowadays we adapted all our instruments are basically the standard equipment we use is that we can measure at several channels at the same time. So the standard, we have 6 channels, which means that we can measure at 6 different points in the process simultaneously, which of course gives a totally different picture of the emissions compared to 10 years back when we were able to measure at one single point at a time. And still that was really expensive. And we are also working with several companies on further development of these technologies. And I really see that the coming years, there will happen a lot. We will be able to measure even better. And especially we will be able to measure trends much more easily than today. Today, often we measure only during a certain time period. And that, of course, is not the optimal way if you want to control the emissions. We have been measuring, and great variety of different processes, mainly in Sweden, but also some measurements abroad. But in Sweden, the main focus, of course, on the conventional activated sludge process. But there we also have different process configuration. You see here some of the ranges that we are measuring. So the nitrous oxide emissions related to the incoming nitrogen load to a process, which covers often quite good with literature values. But you see here, for example, that different configuration of the activated sludge process can also lead to different amount of nitrous oxide emissions. We are working with SBR processes, also MBR process. I will come back to that later, where we see less greenhouse gas emissions so far from that process. We have been working quite a lot with supernatant treatment processes, both nitrification, denitrification, where you see we actually measured quite high emission rates of nitrous oxide. I will come back to that a bit later as well. Sludge handling, of course, there often the methane emissions, of course, are more important, but we also have nitrous oxide emissions in the sludge handling process when it's stored or if it's spread on the agricultural land, for example, which is the common way in Sweden. We have also there the greenhouse gas emissions. The overview here, just to get some comparison of some of the processes we are measuring. All these treatment plants are in the Stockholm area, for example, where we have the MBR process, two different MBR processes. We have the standard activated sludge process, and we have one step load activated sludge process, and so on. So you see a bit, it can vary a bit there. I was mentioned before that nowadays the instruments are quite advanced and robust, so more or less everyone can buy an instrument that is really good in measuring, for example, nitrous oxide emissions. But the main thing is that you have it, and not everyone should just buy an instrument and measure. It's not that easy to measure emissions anyhow. In Sweden, we have some facilities that are placed inside the mountain. So there it's quite easy to just measure the total emissions by measuring in the ventilation shaft. But that's not the normal case in Sweden either. So you have to go out and measure on open basins, and then you use the sampling hood, for example, shown here. And then it's quite important where you measure. You need good understanding of the process and also about the processes leading to the formation of nitrous oxide. So how often do you measure? How long you measure at a single point? The placement of the sampling hood is quite important. Here you see an example of a treatment line at the facility in Stockholm, where it's the same basin, just different parts of the basin, where you see the distribution of the aeration system can differ quite a lot. And that, of course, is quite important if you place your hood. You don't see that if you do the measurements. So it's important that you have a really good contact with the process engineer or understanding of the process. It's important when to measure, the season, what kind of load you have during your measurement, temperature, precipitation, snow. So there are many different aspects you have to consider doing your measurements. As I also mentioned that nowadays we are able to measure at several points simultaneously without that necessarily increases the cost. And that, of course, makes then possible, for example, to measure in the inlet zone of a treatment line, in the outlet zone, and in between, where you will see that the emission rates differ quite a lot in that process. But sometimes you only can measure at one point. You need to have control of the different parameters affecting the emissions as well. Quite important, and especially if you want to base your measurements or you use your measurements for mitigation. If we also come to what to measure and where, when we started with emission measurements many years ago, then we were really into measuring everything. We were using enormous amount of times to really measure in different parts of a process, and which requires quite advanced equipment if you really want to, for example, measure really low nitrous oxide concentration, also in anoxic zones. Now, as you can see here in those two illustrations from two different processes, for example, you see in the blue line, you see the nitrous oxide in the liquid phase, and you see the DO concentration, the gray line, and you see the nitrous oxide in the gas phase. So it's an intermediate aerated process, and you see that even though you have nitrous oxide formation in the non-aerated zones, it's not emitted to the atmosphere. Only when the aeration starts again, it's stripped out. So the main process for the greenhouse gas emission or the nitrous oxide emission is the stripping. But the formation in the process is, of course, very important. If you want to mitigate the emission, you need to understand when is the nitrous oxide formed and when it's consumed. The main challenge is not that nitrous oxide is produced in the process. It's only a problem if it's not consumed again. So there you need to have the measurements also in the water phase to understand these processes. And especially if you want to adapt, for example, the control strategies in your process. We have then done studies, for example, with the Unisense water sensor at one treatment plant in the Stockholm area, Bjerregaard, the second largest treatment plant in the Stockholm area, where it's a facility that is placed inside the mountain. So we were using the ventilation of one single process line, measuring the emissions from the complete line and placing one water sensor in the basin. And then we used these two measurements in order to adjust the parameters in the model you can put on top of the water sensor measurements in order to calculate the total emissions. And you have some of these model parameters, you have to adjust them in order that the model fits to the actual location you are measuring it. And that we were doing, and then you see in the figure here, if you really have adjusted your model, you can use the water sensor that is just like any other sensor placed in the water line to really calculate the total emission, and it follows the actual emissions quite good. But if you don't have a good adjustment of your parameters in the model, it can show totally different things as well. So really important there to understand that you can measure the concentrations in the water, but in order to calculate the emissions, it's important that your model is right for your location where you're measuring. We also used the water sensor, but also our hood measurements in another treatment plant in Sweden, in Norrköping wastewater treatment plant, where we are measuring in the reject water treatment. There actually was one of the first larger process we were measuring in Sweden. It was 2012. We were measuring in the process, and just by accident, it was just selected in a project. And we detected that actually 10% of the incoming nitrogen is released as nitrous oxide. So huge quantities emitted there. Nobody knew and nobody cared because the treatment process was generally operating fine without any problems. So nobody was expecting that there was any kind of problem. By a short-term adaptation of the control strategy of the process developed by us, we could reduce the emissions down to 6% of the incoming load, which was of course an improvement, but we also saw that the process as such has physical limitations that we weren't able to reduce them furthermore. So we commented that they switched the process to another process, deammodification process in that case, an MBBR process, which was by Krüger installed in 2018. And then we followed up with new measurements and saw that actually we could improve not only the treatment efficiency, but also decrease the emissions to below 1%. At that time, we also had a PhD student working there, so we did some additional tests with a pH control strategy. We put in the sensor, adjusted the system for the work, and we're testing different strategies. And finally, we came down to below 0.2% of the incoming nitrogen emitted as nitrous oxide. And that's quite good for a reject treatment process, I would say. As I mentioned, we are measuring in membrane bioreactor. There are not so many measurements available in the world. We have, by our own, we have 3 different MBR processes in operation right now, and we have 1 large MBR process at a treatment plant south of Stockholm in operation. And at all these different plants we were measuring, different configuration, different loads, and so on. We can see generally so far that both the methane and the nitrous oxide emissions are much lower than compared to conventional activated sludge processes, but that the MBR process configuration has an effect on the emissions. And recently measured, we just initiated in a step load MBR process, which is new in the Stockholm area. We see that we have much higher emissions of nitrous oxide. So we don't know yet exactly why, the reasons for that. That's ongoing work, but it shows that the process configuration is quite important. But generally that we have good indication that the MBR process may perform a bit better when it comes to the emission of nitrous oxide and methane. We have been working with the implementation of the greenhouse gases in different projects we are working with. We have for many years, we have together with Xylem developed different treatment facilities for the reuse of water. We have developed 8 different treatment systems, which are in full scale at many places around the world now. Both for the reuse for drinking water, reuse for groundwater recharge, industrial reuse, but also for agriculture applications, for irrigation. And there something that we found out is, for example, that if you only have a partial nitrogen removal, which from the sense of the water reuse is really attractive, and also the costs for the treatment are lowered. So generally it's believed that it's also from the environmental impact perspective, it's much favorable, but actually it isn't. The greenhouse gas emission in such reuse application eats up all the benefits of the partial removal and the irrigation benefits, unfortunately. So it's actually better to treat the water to a higher water quality and then use it for different purposes, also for irrigation, because otherwise the greenhouse gas emission really stand for a really huge environmental impact of these reuse applications. And that is something that I think also today is not really considered in the planning also in the European Union for increasing the treatment for agriculture reuse. We also work together with treatment plants in the development of new strategies. How can these greenhouse gas emissions can be taken into consideration for further development? Here, a treatment plant south of Stockholm, Hubgrade, where we have been doing measurements for many, many years. You see here, if you look at the global balance for the treatment plant, both the indirect and direct emissions from the treatment plant, you see that the actual emissions from the nitrogen removal are the main impact, the nitrification process 60% approximately, and the supernatant treatment 40%. But of course, also the sludge handling has some impact. On the positive side, the treatment plant is upgrading the biogas, is producing biogas, upgrading the biogas and replacing fossil fuel in the Stockholm area. So we have a huge positive effect. And the treatment plant is only using green electricity, which is of course also an impact. And you see, if you look on the total emissions for an inhabitant in the Stockholm area, the wastewater treatment only accounts for 1% of the total emissions. So it may seem a smaller part, but for the treatment plant, we still talk about huge emissions. If you then look at the further development of that treatment plant, that is one of the treatment plants that is reconstructed right now. We did a comparison, and here you see different scenarios. We see the one on based on our measurements. We see one here, for example, where we had inhibition of the nitrification process in several lines. You see that the emissions directly increase quite a lot. If we only take reported literature values, you see that the treatment plants has much less emission values. So literature values are a good starting point if you have no measurements, but you really should do emission measurements. We also see then different other impacts, how you can develop the treatment plant in order to decrease that climate impact. And we see that we also have scenarios which are now also implemented where the treatment plant becomes global neutral. And here we are not talking about taking in external organic waste. If you just increase the amount of external organic waste, increase your biogas production, and by that compensating for fossil fuel, then every treatment plant can be climate neutral. But if you don't consider that as the easier way, you still can do that. And then my final slide, the system perspective, a really important aspect I would like to bring up. We have been working with LCA in all other projects, doing all the time. I was at RVL at least. And it's really important that you have the holistic view. So if we, for example, look at the treatment plant where you have, for example, for reuse in Spain, and you try to reduce the environmental impact by, for example, decreasing the energy consumption by 10%, you get some effect. But at the same time, if you use a different energy mix, the changes are much larger. So don't start to sub-optimize a process to gain some smaller benefits if you can do something else that is more important. And also the greenhouse gas emissions are only one environmental impact. If you look here, for example, on 9 different impact categories that we assessed for our reuse applications, then we see, for example, that the antibiotic depletion is much more important than the global warming potential if we, for example, look at the sewage treatment. And then you have many different other aspects coming into. I mentioned before, for example, the external carbon source is also a source of emissions at wastewater treatment plant. We are replacing right now in one of the treatment plants in Stockholm, we are replacing the external carbon sources with internal produced carbon from the sludge, the digested sludge. And in that way, we reduce the emissions there as well. And the final slide, our team, our team in Stockholm and Gothenburg working with greenhouse gas emissions. So my colleagues here. And with that, I would like to thank you. And please welcome for questions.
Thanks a lot, Christian. Thanks for a great presentation. Great overview of that, really extensive body of research. Really nice to see all these, results from different categories. I'm looking at the chat right now. I don't see any questions in the chat. If anyone would like to ask a question, please raise your hand. There, I've got one. Erik Christian Heyer, please unmute and ask your question.
Yes, hello, this is Eric from Novafos in Denmark. One of your slides, you showed that it was necessary to make off-gas measurements even though you want to install water-based measurement equipment. I think it was 1 or 2 slides earlier than this. Could you elaborate on that? Is it, can't you do the thing with just having the water-based nitrous oxide measurement?
No, you can't. Now, of course, Unisense, you can discuss that later on.
Discuss that one-to-one as well. Yeah.
It's your product. But what we see is that, you can measure accurately the concentration in the water phase, but that you can do with just a sensor. But if you want to calculate the total emissions of the nitrous oxide from your complete process, you have several parameters that are going into that model. Of course, not only the basin dimensions, the KLA, the transfer coefficients. You need all these parameters have to be adapted in order that your model is predicting the correct emissions. And what we have been done in that paper here, for example, is investigating how these different parameters affecting how good the model is predicting the actual emissions or not. And as I said, here we had advantage that we can measure the emissions from the whole process, so we are quite sure. But the same was also in this one here. we were using, the PhD was only using the water sensor to do all the experiments with the pH control. But first, after we adjusted the model for this specific reactor for that sensor, so we had to do the off-gas measurements in order to adapt the model. And then when we know that now it's working right, we could remove the off-gas measurements. And we did it actually after a half year of the testing period. We did just a follow-up measurements, and we saw that the sensor, that the model still fitted without any problem. But the initial adjustment of the model parameters were necessary in order to know that the sensor is actually, the model put on the sensor is predicting the correct emissions. So it's just important that you differ between measuring a concentration, that is what the sensor does, and then the model calculation based on these concentration measurements that are calculating the total emissions.
I see a response there from Mikkel. I'm going to allow that one as a last, and there were two other questions, Floris and Aprilia. Please type them in the chat, and then I will pass them on to Christian afterwards, if that's all right. For time constraints, we can only take this one here.
Yeah. So just a quick comment. So I'm author on the same paper, and actually we show in the paper that we are within plus minus 10-15% of the true value. So of course adjustments will make it even better. We don't claim that we match an off-gas equipment because it's a different measurement, and we also have the airflow uncertainty that goes into the calculation. But other than that, I'm in agreement with Christian.
Good.
Great. Well, thanks very much for the discussion at the end as well. And I will then like to call up the next speaker, which is Sara Ekström. She is working at Baresel in Sweden. And Sara is a process engineer at the Sjölunda wastewater treatment plant, where she manages the project on mapping nitrous oxide and other greenhouse gases, and then with the aim of finding operating strategies to reduce these at Baresel's wastewater treatment plants. So very much looking forward to your presentation, Sara. The floor is yours.
Thank you. Can you see my presentation now?
Yeah, we see it perfectly.
Oh, perfect. Okay, thanks for the introduction, Bastian. And hi to all of you out there who are listening. Very nice to be here today and be able to share a bit of our practical experience that we have from Baresel. It's not as immense as Christian's, since we have just started this, but I think that we have some nice things to share with you anyway. So my agenda for today is to give you a short background on who we are at Baresel and why we are interested in this kind of measurements at all. And that is very connected to greenhouse gas accounting that we have done at Baresel quite recently. And this has been a driver for starting a measurement project at Baresel, where we actually measure our greenhouse gas emissions. And I will share some of our results and what we plan for the future, and also what we have concluded so far within our project. So Baresel is located in the southern parts of Sweden. It's a municipal organization built from 5 different municipalities: Malmö, Lund, Eslöv, Lomma, and Burlöv. And we have roughly 500,000 customers, and we provide them with drinking water, and we take care of the wastewater from our customers. And in some of these municipalities, we also take care of the waste and recycle the waste. And for some years ago, Baresel took on 6 organizational goals, and one of these goals is that we should be carbon neutral and energy positive by 2030. And that's really why we are interested in measuring our greenhouse gas emissions. And of course, this has been a driver for both starting to calculate our emissions, which we have done. And this greenhouse gas accounting has also been like a starter and an eye-opening, I think, for a lot of people within Syd when they have realized from where our greenhouse gas emissions come within the organization. So on total, we have an annual carbon footprint corresponding to roughly 70,000 ton CO2 equivalents. And the wastewater treatment is really contributing to this carbon footprint. We have nitrous oxide that is produced in the wastewater treatment line. It's about roughly 30%. And then we have the electricity that we use at our wastewater treatment plants. That's also a big chunk here, as well as the chemicals that we are using at our wastewater treatment plants. And then a quite big chunk here is also the methane slip that we have from our sludge handling processes. And when these calculations has been done, it's only based on the emission factors. And what we can see here is that we use an IPCC emission factor of 1.6% of the total influent nitrogen when we calculate this. And we have realized, since we have this big chunk of our carbon footprint that seems to originate from the wastewater treatment line, we really need to check if this is valid or if it's worse, or yeah. So that's how we started this project of measuring our greenhouse gas emissions. And we haven't we started our project last year. We purchased this equipment and it got delivered in July 2021, so we haven't had it for that long. And what we have is an electrical cabinet that we can move around on the wastewater treatment plant. And inside this cabinet, we have a gas analyzer where we measure nitrous oxide, carbon dioxide, methane, and oxygen. And connected to the cabinet, we have Unisense sensors that we can use then in the water phase. We have 2 of them. And we also have flux chamber hoods that we have produced based on drawings that EWAG from Zurich were very nice to give to us. So we have 8 of these hoods that we can use, so we can have up to 8 measurements at the same time, or not at the same time, but because we have, this is what the setup looks like. So we have these valves that Christian also was talking about, so 3-way valves, and we have a purge pump that's purging from all besides one of these hoods at all the time. And then the off-gas sample is going into the off-gas analyzer from one of these off-gas hoods at the time. And before the sample is going into the analyzer, it's pre-conditioned. And then, as I said, we have those extra additional sensors from Unisense. And we also have a bit of just regular sensors to check on the process conditions like pH, ORP, and ammonium, and so on. So that's the system that we use. And we decided to start this out at Klagshamn wastewater treatment plant that's located in Malmö. We chose this treatment plant because it's quite small. It has a neat and easy configuration compared to Sjölunda, for example, which is really complicated. So we have inlet screens here, and after that we have a sand trap where we add iron chloride for now I lost the word, but pre-precipitation in the pre-sedimentation tanks. After that, the wastewater continues into the activated sludge line where we have both BOD removal and nitrogen removal. And sludge, the activated sludge is separated in the post-sedimentation tanks, and both sludge from the pre-sedimentation and post-sedimentation is going into the sludge handling, and the reject water from that is going back to a side stream partial nitrotation anemox. And after post-sedimentation, the final nitrogen removal takes place in our post-denitrification MBBR. And after that, we have a final polishing step as a sand filter, and here we can also use some iron chloride if we want to precipitate some more phosphorus before we let the effluent out to the recipient. And what we wanted to do first of all was to kind of map how the emissions were divided in our wastewater treatment plant. As Christian said, we were suspecting the activated sludge and the side stream nitrotation anemox to be quite to have a huge impact on the total emissions. But we wanted to check in all our treatment steps so that we didn't have any recirculation or anything like that gave us any unexpected emissions. Results is that we have the largest nitrous oxide emissions in the activated sludge process, and this was made during summertime, and roughly 30 kilograms of nitrous oxide is emitted per day during this time when we did these measurements. And the methane emissions are fairly small in comparison to the nitrous oxide emissions, and the only place where we really have some methane emissions is in the first treatment step, which is the aerated sand trap. After that, there is not really any methane. And as I think this is quite clear that roughly 81% of the total nitrous oxide emissions really comes from the activated sludge, and then we have 6% from the post-denitrification and roughly 7% from the anemox reactor. And regarding the methane emissions, it's roughly 46% that comes from the sand trap, and the rest from the other treatment steps. But when we calculate the carbon footprint, or the percentage of nitrous oxide and methane that of the total carbon footprint, it's really evident that 99% of the direct emissions is due to nitrous oxide emissions. So these kind of small methane emissions are not that very important for us if we want to do something about the emissions that we have. And what we are also interested of course, is to compare the emission factor that we have at our wastewater treatment plant, since we use a calculation factor of 1.6% in our greenhouse gas accounting at the moment. But what we have seen during the summertime measurements is that we have a factor that is more close to 3% of the influent, and that is actually twice as high as the emission factor that we use today. So this, if it's like this at all our wastewater treatment plants at VA Syd, that would mean that we would kind of rapidly increase our carbon footprint to a large extent. And as a second part of this project, we have been screening the activated sludge plant because, as we heard before, it's these emissions are not going to be equal all over the activated sludge line. They are probably changing, and I mean, with changing, I mean that they will not be the same in the inlet and the outlet. And we chose to put 4 hoods in one of each activated sludge trains to see what this gave us. And we can see that as we move further away from the inlet, so the black line here, that's the first zone 1, and then this gray is zone 3. That's a bit further away from the inlet. Blue is zone 6, and the green curve is the last zone in the activated sludge train. And as we see here, the concentration of nitrous oxide in the off gas increases the further away we get from the inlet of the reactor. And its dynamic changes over time, and it's not the same in the 2 trains. So this is train 1 and this is train 2. And these measurements were performed during winter, and we actually have much lower emissions during these months. So an emission factor that's only corresponding to 0.6% of the nitrogen reduced. So that's a quite big difference between summer and winter time here. And then we also are interested in how much nitrous oxide that's leaving the reactor with the effluent, and here it's roughly 3%. We always have this nice correlation between the off-gas measurements and the liquid phase. And if we would like to use the sensor in one of the zones where we don't have a sensor, we could always use this kind of correlation, and we can also calculate KLA based on when we know that we have a measurement, we can do that. But we need, I think that, yeah. So that's also something that we would like to do. And the nice thing with the sensor is that we can always, we will always be able to keep track on where nitrous oxide is produced versus where it's emitted. So the conclusions that we can draw until now is that the nitrous oxide emissions, they stand for 99% of our direct carbon footprint at Klagshamn's wastewater treatment plant. And we have a emission factor that's 3.2% of the incoming total nitrogen. And this would really increase our carbon footprint if we compared to the IPCC emission factor that we are using in our greenhouse gas accounting right now. And quite as we expected, the aerated activated sludge process is the largest contributor, and that's really where we should focus our further measurements. And what we would like to do next is to gather long-term data, and that's to have this I'm sorry.
Sarah, we lost your sound.
Yeah, Sarah, we don't hear you anymore.
3%.
Now we're back. We just lost the last minute because there was a difference in there was a delay. Maybe you could just go back and just repeat that, please.
Yeah, so we would like to have the long-term data set just to since we have seen those differences, and I think that's also what's really pointed out in literature, that to be able to say that you have an emission factor that amounts to a certain percentage of your influent nitrogen, you really need to have a long-term data set. And we would like to continue this data analysis that we have started, and that's to find or use this as an input for a modeling study where we would emphasize on mitigation strategies, and hopefully we will have a collaboration with Lund University on this. And what we really would like that modeling study to give us is some kind of full-scale operation strategies that we could test at Klagshamn wastewater treatment plant. And after that, we also need to implement our measurements at remaining, because now we are at one wastewater treatment plant and we have 5 that's quite large, and then we have also a whole lot on the countryside. But we will focus on the bigger centralized wastewater treatment plants for now, I think. Yep. Thank you.
Thanks very much, Sara, for this great overview and exciting research and exciting journey ahead still. While it's of course alarming to find these high emission factors, I think it also gives a lot of room for optimization. So you have interesting work ahead, and yeah, thanks a lot for sharing that with us. I'm sure that many people can benefit from it. Do we have any questions from the participants or from the speakers as well? Of course, if there are any, please raise your hands. While people are still thinking, I actually have one myself. You showed very clearly in your activated sludge process that you have most of the emissions towards the end of the zone, which is actually unusual, I think, from what I've seen so far. Usually it is more in the beginning where you have a higher turnover, or the highest turnover of ammonium that you would see, high nitrous oxide. Do you have any indications or any gut feeling, any ideas as to what is going on there?
We think that it's because it's a quite high-loaded plant. So most likely because the emissions are also kind of low in the first zone. So we think that it's only BOD that's actually being oxidized in the first part of the activated sludge, and then the further away we get from the inlet, the more nitrification is going on.
Yeah, okay, that makes good sense. Thanks. I have a question in the chat from Maria Dittmann. I'm just going to read that out at Sara. You mentioned that methane emissions were not really relevant for the wastewater treatment plant. However, as far as I've understood, you have only looked at the water side and not at the sludge treatment, where relevant methane emissions would mostly appear. Is it also planned to have a closer look at the sludge treatment?
Yes, but not within this project. Maybe I should have been clearer on that. So this project only aims at looking at our emissions from the water line at the wastewater treatment plant, and then we have another project for looking at the sludge line.
To get the full picture afterwards. Yeah. Okay, that makes good sense. Then I have a question from Plano, from Salvatore, Salvatore Plano. If you would unmute yourself and ask a question.
Hi, Bastian. Hi, Sara. Well, very impressive research work, and so I basically called this morning from UK, but originally from Italy. The question I have is actually same as you did, Bastian. It's related to these high N2O emissions on the back end. I was wondering if is related to the diffusers configurations and gas velocity. So sometimes the design is not very optimized. You have a high gas velocity on the back end. So
no, actually, oh, sorry.
Yeah.
Actually, the aeration rate is lower at the back end than in the beginning. So when we first started, I didn't show all the data that we have, but we did very short mapping first to kind of have a gut feeling in which zone that we should put our flux chambers. And then we could see that, so our first impression was that we were going to have the highest emissions in the beginning, actually, or in the end. But then when we started to do the calculations, it's somewhere in the middle that the actual emissions are going to be the highest on a long term.
Thank you.
And that's also that would be quite typical then for what we see, that about 1/3 into the aerated zone, which is a very good representative spot to actually measure in many treatment plants. I have one last question that I can still allow from Ellen. Please go ahead.
Yeah, probably not a question, but just a comment. And probably the reason you see this high emission in the middle, I think that fits what you said, that in the beginning you have BOD removal. And then when you start with your nitrification, it happens at the highest ammonia concentrations. And I think that's by the end, the ammonia concentrations are much lower. And I think that explains that you then have there the lower emissions than compared to the ones in the middle.
Yeah, that's probably also a factor.
Yeah, what we saw in the Netherlands in 2010, we did some lab experiments, and we saw the highest specific nitrous oxide productions at the highest temperatures, so at a high conversion rate. So, and if you translate that to monokinetics, is the higher the ammonia, the higher the oxygen concentrations, the higher the specific nitrous oxide emission rate, production rate. So I think that actually from what you've told, I think it's quite a plug flow character of your.
Yes.
So I think that's really concentration driven. Then where you have the highest ammonia concentrations, you can expect the highest N2O emissions.
Thanks. Thanks for that comment, Ellen. It shows that great minds think alike, and coming together confirms our things of way of thinking. I have one last question again in the chats. People are just really curious about your research, and we have time for this one. So the question is, thank you for your interesting presentation. Was the 3.2% factor based on the data from different seasons? And did you see a large difference between seasons? You might have talked about this, but I have some connection issues which caused me to miss some of your presentation. Okay.
Yeah, so the 3% was mainly from measurements during summertime. And then when we made this mapping more intensely in the activated sludge, we actually only had 0.6% as emission factor. So we think that it will vary over different seasons, and that's also why we want to do those long-term measurements at the wastewater treatment plant.
Yeah. Great. that concludes, I think, the full picture. Thank you so much, Sara, for being available for all the questions and discussions as well. Yeah, we can then continue with the next speaker. The next speaker is Mikkel Algren, Stokholm-Bjerregaard. I sort of pronounced it well, and not quite perfect. He works at Krüger in Denmark, and Mikkel is heading there the wastewater innovation team, where he's working with wastewater digitalization, smart controls, also including direct greenhouse gas emission reduction, and combining these into the automated control system called Hubgrade, which he is going to tell us about in his presentation. So yeah, very excited and looking forward to that, Mikkel. And the floor is yours.
Thank you very much. And you all see my screen now?
Yeah, we see it perfectly.
Excellent. Well, great. Thanks for inviting me to have a chat here. I'm looking forward to it. I want to tell you about, as you said, Bastian, surveillance and control of N2O emissions as part of the Hubgrade performance plan. And so now we are slightly moving over to the control part of this interesting emissions theme. Just very briefly from the beginning, for those of you who do not know what Hubgrade performance plan is, it's optimization as a service. It's a way to control and operate primarily wastewater treatment plants, while focusing on many aspects at the same time during this this operation, in incorporating both water quality, chemical dosing, biological capacity, energy savings, hydraulic capacity, and so on and so on, and of course also CO2 equivalent and carbon footprint. So it's a holistic approach to online control of wastewater treatment plants. It's cloud-based, so it's the advanced treatment algorithms takes place on a cloud-based server and communicates with the PLC or SRO system at the plant to convey these set points for the control. There are many different individual controls that can be selected and to fit each and every individual plant. And what's most relevant with the CO2 E equivalent here is, of course, secondary treatment as part of the biological process. There are many full-scale reference around the world, so it's a well-tested system that's been operated for many years and just recently moved to be cloud-based. Okay. So what's actually the core of this control is actually controlling the oxygen set point and the phases or the zones or the aeration duration of these treatment plants. As you can see here in the bottom, we see normal fluctuations between ammonium removal and nitrate production, and this is of course a result of the aeration of the treatment plant. The trick is then to balance this to best suit the maximum overall removal of total nitrogen, and to do so with the least energy consumption, and of course also the least N2O production. This control includes criteria for when the nitrification and denitrification phases are engaged and closed, and also creates set points for the DO aeration. As part of this, there is a N2O minimization feature included as a standard part of this project. Product. When installing a sensor such as the Unisense N2O liquid sensor, a very simple and standardized but very effective and robust control feature is automatically implemented and can be just simply turned on by request. The very essential feature of this control is that when a certain N2O limit is reached, that's set in settings, simply aeration is stopped and denitrification is engaged. And in essence, what this does is that it aborts emission and it initiates N2O denazification. So stopping the active emission and thereby stopping the problem, and also removing the cause of the problem by denazification. So this is quite a simple trick to control N2O emissions that can be applied in almost any wastewater treatment plants, and is very effective and very robust in the way that it works. But that's of course not all, because as we've learned, many parameters affect the N2O emissions of a treatment plant. And here the holistic approach comes into how we control wastewater treatment plants. Because as I just briefly mentioned, the DO and N removal, the control of the phases and the DO set point is very important also in order to balance rates, for instance. The mixer operation is applied to minimize DO gradients and reduce N2O productions, and also facilitate denazification as an N2O sink. Similarly, solid retention time control adapt sludge age to actual loads and capacity of the plant, and balancing the appropriate amount of sludge in the treatment plant to the actual load of the plant is also a key parameter in order to minimize N2O production. Return activated sludge control, increase hydrolysis at the bottom of the settler and in the tubing, minimize nitrate return, both to facilitate denazification as a sink to N2O. The recirculation for those plants also is a control to balance the nitrate concentrations and facilitate denazification as an N2O sink. Finally, the carbon management, if that's in lack and you have problems with the insufficient denazification, carbon addition is a way to complete the nitrogen removal and facilitate this removal of the root cause to emissions, right? The actual liquid N2O concentrations. So all of these act together in a holistic way to overall minimize the N2O production and emission from a treatment plant. This right here is an example from a treatment plant in Denmark, where we did a very brief test to illustrate here the effect of this very direct control to N2O mitigation, where aeration is aborted and denazification initiated when a certain limit value to the liquid N2O concentration has been reached. And on the top here, you see the N2O concentrations in the liquid phase, and in the bottom below, you see the activation of this control feature, the N2O mitigation feature. And in the green framed circles, this control has been activated, so we've crossed a certain threshold limit with N2O in the liquid phase, and this activates the control feature, which then aborts aeration and initiates denazification. And so here in the green phases, you have smaller peaks in the N2O liquid phase, whereas in the red ones, where you do not have this activation of the control, the peaks are higher, and thereby also emissions are higher. In this specific case right here, we saw reduction potentials of up to 70 to 90% of this right here. We've been talking also about emissions and emission factors. As part of this product, we have a standardized solution to also calculate the N2O emissions based on the excellent work that Unisense has done on this. And based on their guidelines, we use this in the online control to do the calculations of the actual emissions. This here is an overview, and in essence, the needed settings is just put in as part of the user interface, covering tank depth and diffuser area and stuff like this. To zoom in right here, we see an example of the actual emissions online and the cumulative emissions over time. We also have a division into emission depending on whether or not you have emissions in the aerated periods or the non-aerated periods. And finally, you have, of course, the actual N2O concentration measurements in the tank. So all of these things together to keep track. We, of course, want to further improve the control opportunities that we have to offer in addition to this N2O mitigation with the N-phase abort function. And we are currently involved in several research projects to develop this further. One is what we call the biokin in DNA Fantastic, where we actually use DNA measurements of the microbial communities of such a system to connect with the biokinetic performance of the plant, and using this for control of activities of the nitrifiers in the plant to maximize nitrogen removal, but minimizing N2O production. In another project, we developed deep learning artificial intelligence tools to be able to predict N2O production into the future. So we will be better prepared to control and mitigate the future N2O production and even improve the control based on that. That's my time spot right here. I'll invite any questions from the audience.
Thanks very much,
If there are
Mikkel.
any. Yeah, no worries.
Wonderful presentation. Thanks a lot for giving us these insights. I will look at the chat for questions. Don't see any right now, but probably people are still coming up with them. I have a question that I'm curious about. Krüger is, of course, a Danish company within Veolia as a global company, global player. And Denmark, as we know, is sort of at the forefront also legislation-wise in nitrous oxide. Maybe you can elaborate a little bit on how many how the adoption of this module specifically in Hubgrade is coming forward in Denmark and maybe in other countries, and what your ideas are for the future. What your feeling is, where and which drivers there will be in other places in the world to adopt this.
Yeah, interesting question, and very relevant. Also, one of the challenges that the climate has is the drivers in the regulatory sectors, right, around the world. There's a lot of interest on N2O. Many places around the world, they recognize that this is an important parameter to look into and to develop controls for. Drivers are few around the world still, especially economic drivers, right? So it's mostly strategic, ethical drivers that push clients and collaborators to do activities in this. Veolia has taken upon, because they also operate a lot of plants around the world. It's different from what we're used to in Denmark and Sweden, where independent water utilities operate the plants themselves. Around the world, they, in many places, hire in, for instance, Veolia to operate the plants. Veolia has a strategic commitment to, from now on, in a what's it called? It's in a deliberate, step-by-step way, will include an online control, including N2O mitigations, stepwise in all plants above 50,000 PE going forward from now. And we will always offer solutions, alternative solutions with lesser carbon footprint than what's requested. We will also propose alternative solutions with lesser footprint, and this will in many cases include some activities regards to N2O.
Yeah, sure.
But that's a strategic commitment on our side.
So it's the holistic view. That's a good point. Well, two questions in the chat. One from Amanda Lake from Jacobs. She says, interesting control concept, Veolia. Have you tried the N2O concept in any sustained manner, long-term manner, and been able to maintain the process and effluent compliance across a longer period of time? What were the wider impacts on the plant?
Yeah, thanks, Amanda, for that. That's a wonderful question. We are currently doing long-term tests on this. It is a challenge, to be very frank, that the drivers are not there. So many clients are interested in developing tools, testing tools, monitoring their emissions, but less are directly motivated right now to actually spend a lot of effort in operating the controls, right? Because the financial drivers are not quite there yet to do this. So that's why this project process is rather long. We have some that we work on now and hope to be able to present this soon.
Great, looking forward to that. There'll be one more question. There's actually two, but I can only allow one more. That is from Sebastian Schmuck from Germany. Great talk, thank you very much. Would you be so kind, tell us something more about the project DNA Fantastic? And if you could keep it sort of brief to 1 minute, that would be great.
Well, in essence, the target is to correlate the activity of the nitrifiers to the actual N2O production, and by then developing tools to deliberately control the activities, we can also deliberately control the allowed N2O production this way. And the fundamental new input to this is that we are able to facilitate really fast DNA measurements with a weekly turnover and fast results response on this. So within a week, we have continuously new sample results from DNA analysis of the activated sludge in the plants, and we incorporate this directly into the online control system that also handles the N2O measurements, the emission calculations, and the operation of the phases. So that's the pieces we are putting together in this project right here, together with the 3 municipalities here in Denmark. Please contact me if you want to hear more on this in another setting with more time.
That's a very good point. Yeah, and thanks very much. There's a few more questions, Mikkel. We will answer this in the chat. I think it's a very general question that we can get to in the chat. Yeah, but looking at the time, I will call up our last speaker, my colleague Mikkel Holmen Andersen. He is CTO of Unisense Environment and has been responsible for the technical development of the liquid phase N2O measurement system. He always said that he comes from a background of biotechnology and then has chosen the biggest bioreactor in the world out there, which is the wastewater treatment plant, where he's now been active for about 11 years and gathered a lot of experience. And yeah, Mikkel, very much looking forward to your talk. The floor is yours.
Thank you. Can you hear me?
Loud and clear, yes.
Okay, so just a brief 10 minutes on what we can actually do once we have the measurements. For the last 4 years, there's actually been a big push here in Denmark to gather more data on greenhouse gas emission, especially nitrous oxide. And from 2018 to 2020, we had a nationwide monitoring campaign running over 2 years, where both big and smaller plants were monitored, measuring nitrous oxide using both our equipment, but also off-gas equipment in some cases. And the goal of this was to actually improve the national emission factor that we in the UN system are obliged to provide data for to the IPCC global CO2 footprint reports. And what was found, and what has already been said by other presenters here, is that first of all, the nitrous oxide is really varying between different plants, but more more also the deammonification type of processes comes out as really a high emission type of process. Another learning that we had was that it's actually the bigger wastewater treatment plants here, the two of the three bigger plants around Copenhagen, they have emission factors that are sometimes much higher than even the new emission factor in Denmark. So the point really is to monitor for a long time and actually monitor every wastewater treatment plant in order to know what the emissions will be. What is also important is that in order to cover the most of the wastewater treatment plant, the Danish regulation that will come in place now will actually focus on the plus 30,000 PE wastewater treatment plants, where we will actually target around 50 to 65% of all of the wastewater treatment plant, wastewater treated. One of the key parameters, and I guess many of you are process engineers, is that actually energy consumption, which is actually one of the bigger carbon footprints, unless the power is green, that saving is actually coming from advanced process control. And these advanced process controls, as you've seen before, are actually also the same that we need to mitigate nitrous oxide. So carry this with you as a take home, that actually power savings is also coming from efficient and advanced process control systems, and only around 30% are coming from buying new equipment. And there are several big vendors that have actually done these analysis and shown that the savings are also coming from the controllability of their equipment. Here it's a picture of actually the N emissions per day from a wastewater treatment plant in Copenhagen. And as you can see, this is just the month of April in 2019. And if you do short-term campaigns in a month like this, you will get very different data comparing, mid of April and then the end of April. Here you can see how different the emissions is. And actually in this case here alone, we had quite a higher emission factor, so 1.6% of the N that comes in. But looking over longer term as well, if you monitor for 1 year, 2 years, actually we've been monitoring for 4 years. From year to year, there's also a variation. So here in 2019, it was a much higher emission compared to 2020, and 2021 was very much like 2020. And no changes in controls were made in this part here of the data. And you can see on this plant here is actually the spring months where we have the biggest emissions. So one key element, and that was actually mentioned before by Ellen from Royal Haskonen, is that it's well proven that the amount of ammonium that is turned over per time per gram of activated sludge is really important in terms of the emission. And it's been shown that if we turn over a lot of ammonium in a small volume per time, then we will have a much higher emission compared to one where we have less load on the same amount of sludge. So we can have if we have high SS, so high bacteria content in the tank, then we will actually lower the substrate concentration and consumption per volume, and then we will also get a lower emission. And we actually tested this in full scale for a whole spring in 2020. And here you can see the cumulative emission in 2 tanks of 4, and the red ones here are the ones where we didn't change the SS amount. And you can see the green one here is then the SS content, which was just kept 0.5 to 1 gram per liter higher compared to the control. And you can immediately see that the emissions are getting quite low from the start, and they actually stay very low. And then if we also try to optimize in terms of the DO, then we can immediately see that we'll get a response, in this case here, a negative response. So if we start to suffocate the bacteria on top of the reduction of the substrate, then we will actually get higher emissions as well. And then when we return to a normal situation, then we will have more or less the same emission. Here's again the cumulative emissions. So overall, actually, just over this spring, we actually saved around 80% of the total emission, and that is the equivalent of around 16,000 tons of CO2 equivalents per year that was mitigated by this simple control. And looking at load, this is data now from Vandcenter Syd here in Denmark, where they compared, two tanks dividing load compared to two tanks in series, where the first tank take all of the load and then is passed on to the next. And as you can see, dividing the load into two tanks rather than having a much higher load on one tank shows the same picture as we saw before. The green ones here are where we are having most of the load on the first tank, and you can here see that the emission is significantly higher than if we split the load into several tanks. So load balancing and having higher SS are two really cheap and easy ways to do mitigation. We have also played with both pilot scale in this case here, but also full scale changes in terms of variation strategies, and also trying to see if we could get simultaneous nitrification, denitrification to work. And here it's a 2 cubic meter pilot plant. These are data back from 2016, where we first ran an alternating aeration strategy, keeping the ammonia at a steady level, and then after 14 days, then we changed to a recirculation strategy where we tried to stimulate both nitrification and denitrification at the same time. And you can see as we lower the DO, we still comply with all effluent values as we should. The nitrous oxide is also much lower, and we actually achieve both an energy saving but also a reduction in the emissions. In this case, around 26%. And actually, last year we ran this in full scale in a 80,000 PE plant at Skanderborg, where we actually halved the emission and doubled the capacity on the plant by implementing the control that you see here. A key is that we need, high controllability in order to maintain this simultaneous nitrification, denitrification process control, because otherwise it will not steady. We can also use the nitrous oxide sensor to dose carbon, and as you heard Bastian Baresel telling you, internal carbon sources can also be generated. But actually, if you do polishing steps where you use a post-denitrification tank, then you can actually have a fair bit of emissions of nitrous oxide. But actually, what we showed is that if you measure the nitrous oxide as a function of the COD that you add to the tank, you actually get a very beautiful picture of the stoichiometry of the denitrification. And with cell growth, we need around 2.5 molar of COD per mole of N that we remove, and actually dosing carbon exactly to this actually shows that the emission then disappears. So carbon dosing using the nitrous oxide sensor is also a possibility. And then one of my last slides, that is for the deamplification. This is data from Aarhus Vand, where they actually changed the classical pH control on a demon plant, and then changed the input rather than pH to be a control where they had a simple feedback of the nitrous oxide sensor to the blower, keeping a continuous aeration in check by measuring the amount of nitrous oxide and having a steady aeration. And here they actually reduced the nitrous oxide emission by a factor of 6 by changing the control strategy. So in all, together with many of the partners and some presenting here today, we've shown that not only monitoring is possible, but also reductions are possible, both based on the sensor, but also monitoring while you do process optimizations. And these can be very cost effective. And if we do get a carbon tax on CO2 emitted, then this is for certain a go-to solution for decreasing your taxes. And finally, our recommendation is sorry.
We lost you for 10 seconds.
Yeah, I need just to get back on my I cannot click on my slides right now, so.
You are on your last slide.
Yeah. Okay. Yeah, I just couldn't see it. So our recommendation is. Sorry.
No, go ahead.
Can you hear me? Yeah.
Yes. Hear you.
So reducing energy consumption is of course first, but then the mitigation nitrous oxide is really the next go-to option before you actually do anaerobic digestion. If you do anaerobic digestion, then try to produce sustainable energy that can be transported elsewhere to as biomethane or as hydrogen or some other source of energy. So thank you.
Thanks very much, Mikkel, for giving that overview. Are there any questions from the audience? If so, please raise your hand. Otherwise, I have a question in my own interest a little bit. What do you think will be the next 5 to 10 years at Unisense Environment, and how do you see adoption of measuring globally?
Well, I'm very much on par with Mikkel that this is largely driven by regulation, and currently the EU frame directory for wastewater is under revision, and here we hope to see that for the water cycle that the carbon footprint from here will actually be included as part of the goals. But it is also clear that there are the ability to purify wastewater is there's a gradient across the world in terms of how far you are, and we need also to allow developed countries to get up to a standard where sewage is treated energy efficient but maybe not climate efficient, because that overall will also reduce the carbon footprint. But I believe in the next 10-year frame we will see that the regulation will be in place in Europe and maybe Northern America and Asia for emissions from greenhouse gases from the water cycle as well.
Yeah, maybe even carbon taxing could be a strong incentive. That was also what
that has been shown by many economics. Yes. That is the real driver that will actually make a change, and we know this from petrol gases and all other types of taxes. So it's a matter of implementation.
The pain needs to be felt, isn't it, before it big things are moving. But it's great that many people are working on this topic nonetheless, simply as we've heard for ethical reasons, for reasons of doing the right thing. I think we have a great example of that today. We're also going to end this webinar on time, which I'm quite happy about. We're not going to steal anybody's agenda massively. I want to end with a massive thanks to all the presenters who have spent their time, spent their energy and efforts on preparing these presentations, giving them today. I think it's really a big strength of our water sector that people are open to collaborate and take the effort of sharing what they know with each other. So let's keep that open, and feel free to connect with anyone that was presenting today. Of course, feel free to connect with us directly by email or through our LinkedIn channel. And as I mentioned, next week, Mikkel and I will be at Jönköping at the BA Messen. So if you are around, come visit us at the Danish Pavilion.